Hello. Today what we're going to talk about is the definition of congruence and some of the basic properties. So if we look at our objective, students know the definition of congruence and the related notation. So I put this in yellow, highlighted in yellow for you, and it's basically an equal sign with a little squiggly on top. Make sure you understand that that means congruence, which is similar to equality, but definitely slightly different. So make sure you understand that there's a difference between equality and congruence. And then the rest of this is students know to prove two figures are congruent, there must be a sequence of rigid motions that maps one figure onto the other. And that's really what ultimately makes congruence, is that one figure, and we don't know anything about it other than that the figure maps onto or matches up exactly with the other. Okay? So as you look at this definition, we're really just working on understanding basic congruence. And so our vocabulary for this will be congruence, rigid motions, sequence, composition, translation, rotation, reflection, and to preserve. And our exercise starts off with describe the sequence of basic rigid motions that shows that figure S1 is congruent to figure S2. And so as I'm looking at this, what I'll notice first is that, as I'm looking at this, the first thing that I would notice is that the orientation of the two shapes is different. And automatically that indicates to me that I need a reflection at some point in the transformations that I'm going with. Okay, so really quickly, if I translate along this line that connects the two tails of this, that is one way to get the two shapes identical or lined up. And then what I can do is I can sort of look at the perpendicular bisector of each of the points, or really the line of reflection, and it would kind of go diagonally through. So it would kind of go right through these. And if I reflect over that line, what will happen is one will line up with the other. And so as we're looking at these and we're trying to describe the transformations, one description that would work is a translation and then a reflection. Okay, you might wonder, well, does order matter on that? Well, you can try and reflect it. And so if I were to say reflect over that straight part of it and then try to translate, you'll notice it won't work. So there is a very, very specific line that would work. You could pick one that is parallel. So it should work if I were to draw this sort of 45-degree parallel line to the one that we know works. If I reflected this way first, it would come out like this, and then I would just slide it up. So one takeaway of this would be that it is a very specific line if I'm going to change the order to which I do these. Okay, the next image I'm working with is the number 2. So the red one, can I get the red one to go on to S3? And as I look at it, well, first thing I would notice is that the orientation is the same, implying to me that I'm down to rotation and translation. The next thing I would notice, though, is that the points line up and they're not exactly split by a perpendicular bisector. In other words, I couldn't just pick a point, say down here, and rotate it around and get those things to line up. It would never quite, it'd be a little bit twisted at all times. Okay, so what I first would want to do, or what makes it easiest to probably see, is that I would translate along the vector from tail to tail. Once I'm tail to tail, my center of rotation would be at the point of that tail, and then I could just rotate it along. Okay, so this would be a translation with a rotation. And in this one, order ultimately wouldn't matter because you could rotate it around and then slide it along the same vector. Okay. The last question is describe the sequence of basic rigid motions that shows that S1 is equivalent to S3. And so we worked on making S1 into S2 and then S2 into S3. And so I know that it would be a translation with a reflection and then potentially a translation with a rotation. The question is, can we do it a little bit quicker? And so if you start with 1 and I want to get it to 3, could I do it any quicker? Well, I actually can. I can go tip to tip with the translation, and then I could rotate around, but as you see, the rotation's not going to get it so it lines up exactly. And then I could reflect it. So this one is going to combine all of these, and I can sort of group the two translations together into one vector. So adding vectors is not something that we're going to work with today, but essentially that's what you would do. So I could translate, I could then reflect, and then rotate. And to be honest, each of those could be done in any order. The key to this, though, is that each of these are rigid motions, meaning that angles and lengths stay the same, and I'm setting myself up with the ability to prove congruency. Okay. The next part asks us to perform the sequence of a translation followed by a rotation of a figure, where t is a translation along a vector and AB is a rotation of d degrees, which means you get to choose d around the center. Please label it x prime, y prime, z prime. And so first thing we need to do is we need to translate it. We need to translate it along this vector. So I have this protractor. It's going to allow me to translate. So I just have to get it right on that point. And so there's one arc, probably need a little bit more. Here's the second arc, and here's the third arc. Okay, so I'm going through these just as a review because I know a lot of us have struggled throughout the unit on our constructions. Then the next thing I do is I match up point A with X. That's dead on. And now I can do the B. And so I need this arc here. Then I match up A with A with Y, move my needle point to B. If you're not sure about the reasoning behind this, please come ask your teacher. It's really important that we understand these. Oops. And then I need A to Z. A to Z. So we'll put that on B. Okay. And oftentimes on our papers, we're never sure, like we've got all these arcs. Just be very, very careful. This one went with X. This one went with Y. And this one went with a Z. And so we have this next image. Looks something like this. And then we need to do one more transformation and make sure that that's probably an arc. Okay, and then we need to rotate that around O. And so rotations can be one of the more complicated things. The first thing I really need is the angle with which I'm going to work with. So you need your protractor. Give yourself an initial line between the point of rotation. Let's just go with a 50. Actually, this is going to be negative 50 because I'm rotating. So negative 50 because I'm rotating clockwise. Okay, clockwise 50 is the same thing as negative 50, something to make sure you understand. So we'll do one angle in blue, do one angle in green, and one angle in pink. That way we can just see them a little bit better. Okay. Each of these being 50 degrees. The next thing we really need to make sure we do is have the distance from the point of rotation out, and then get that equivalent. So I want to make sure I have that next one. So there's one of my points. Then I have this Y value. And then the pink. So we have a point here, here, and here. And so this is the combination of a transformation or translation with a rotation. It's good to make sure you understand how to do these constructions and really think about what is the role of the zero or the circle in doing them. And so this is x prime, y prime, and z prime. And then the question is, are the two triangles congruent? Well, they have to be, because based on our definition of congruence, one has to map on top of the other, which it will, since angles are preserved, distances are preserved. So x, y, z is congruent to x prime, y prime, z prime, since rigid motions preserve angle measures and segment lengths. Okay, the last thing I'll put up here are just some lesson summaries, so pause it, write these down, make sure you understand them, and thank you for your time.